Hi, everyone. You certainly remember the formula for x plus y squared. That's x squared plus 2xy plus y squared. You may also remember or heard of the formula for x plus y cubed. That's x cubed plus 3x squared y plus 3xy squared plus y cubed. You may wonder if there is a general formula that will allow us to compute things like x plus y to any power, such as 100. And there is one. It's called the binomial formula, and that is what we're getting at today. Let's try to rediscover the binomial formula on the example of x plus y to the power, for example, 5. X plus y to the power of 5 is the product of 5 terms, x plus y. Let's call these terms factors. 5 factors here. 1, 2, 3, 4, and 5. And now we would like to expand these factors, multiply everything out. It will be a huge, huge sum, but it will simplify because some terms in this long expression are similar, and we'll collect the similar terms, and that's how we'll discover the binomial. What terms can appear if we expand this expression? The term y to the 5 will appear. But if you multiply y by y by y by y by y. So in the expansion, if you expand this thing, this term y to the 5th power will appear. What else can appear? X y to the 4th can appear. X to the power of 1, y to the power of 4 will also appear if, for instance, you multiply x by y by y by y by y. X squared y cubed will appear too. For instance, if you multiply x by x and then y. There will also be x cubed y squared if you multiply, for instance, y x y. 3 x's and 2 y's. And also the term x to the 4th y to the power of 1 will appear, and x to the power of 5 will appear. And that's it. No other terms will appear if you expand this expression. Do you see that? As you expand this expression, it will be a long sum of monomials, of things like this. The sum of these powers must also always be equal 5, and that's because we're multiplying 5 terms here. So this is 5, 1 plus 4 is 5, 2 plus 3 is 5, 3 plus 2, 4 plus 1, and 5. And therefore, these terms are the only terms that will appear if you expand this big expression. Is this the answer to our problem? Not quite. And that's because each of these terms, such as this one, will not appear once as we expand this expression, but there will be lots of similar terms like this. And we need to find out how many. How can this term x squared y cubed appear as we expand this expression? It will appear when we choose 2 factors for x, and the rest will be for y. For instance, this way, xx, y. As we multiply this, we'll get this factor once. But that's not the only way it appears. It could appear, for example, if we choose these 2 factors for x, and the rest of them for y. Or if we choose these 2 factors for x, and the rest 3 for y. Many ways this term can appear. How many exactly? We just need to count the ways in which we can choose 2 factors out of 5. for x, the rest will automatically be for y. So how many ways are there to choose 2 factors out of 5? That's 5, choose 2. This is how many similar terms of this form will be in that expression. Similarly, for this term, the answer will be 5, choose 3. This is a number of ways to choose 3 terms for x, and the rest will automatically be for y. And similarly here, it will be 5, choose 1. It's a number of ways to choose 1 factor for x, and the rest for y. Here is also 5, choose 1. And as for the term, let's say x to the 5, it will appear only once. It will appear only once by multiplying all x's. This is the only way the term x to the 5 can ever appear, by expanding this product. So this is our result. And if you compute the binomial coefficients here, you'll get y to the 5 plus 5xy to the 4th plus 10x squared y cubed plus 10x cubed y squared plus 5xy to the 4th plus x to the 5. That is the binomial formula for x plus y to the 5. In a very similar way, we can treat any power instead of 5. Just replace the power 5 by a general number n. The pattern is clear. All binomial coefficients will appear lined up. Let's write down this general formula known as the binomial theorem. And it holds for any, and this is a letter for any, x and y, real numbers, and for any natural number, which is a number 1, 2, 3, 4, and so on and so forth. X plus y raised to the power of n will be a big sum. This is a letter for sum, going from 0 to n. K denotes the term here, and the terms are of the form x to the k, y to the power of n minus k. That's because the sum of these terms must be n. Just like the sum of these terms is always 5. It's the sum, and the coefficients, as we know, should be n, choose k. That is the formula that's called the binomial formula or binomial theorem, and that's where the binomial coefficients got their name from. One cute consequence of the binomial theorem occurs if you take x and y both equal 1. The left-hand side of the binomial formula is 2 to the n, and the right-hand side is just the sum of all binomial coefficients. An amazing fact that we discovered is that the sum of all binomial coefficients equals 2 to the n. This fact would be difficult to prove directly if you just write the binomial coefficients in terms of the factorials and then sum them up. There's probably no way to directly verify that this long and complicated sum equals something as simple as 2 to the n. But we did it indirectly. Let us give one more proof of this corollary, a combinatorial proof. We can realize both sides of this equation that we would like to prove, as the number of ways to choose any subset of n friends for your party. Indeed, if you line up all of your n friends, 1, 2, 3, up to n, and you decide whether to invite them or not, each of them, without regard of how many, then the number of possible ways will be 2 to the n. For each friend, there are 2 ways, invite or not invite. For that friend, 2 ways, invite or not invite. And the multiplication principle shows that you just have to multiply all these 2's together n times to get the total number of ways who you invite and who you don't. So 2 to the n is the number of ways to choose any subset of n friends for the party. Alternatively, you can decide beforehand how many friends do you want to invite. Let's call this number k. The number of ways to invite exactly k friends is n choose k. And now, if you want to make a k arbitrary, you just sum up all these ways. So both sides equal the same thing. They just count the number of ways to choose a subset of n friends for the party. Therefore, these 2 sides must be equal to each other. And that was the alternative proof of this beautiful equation. Another beautiful combinatorial identity is called Pascal's rule. It gives a recursive formula to compute all binomial coefficients. For any n and k, the binomial coefficient n choose k can be computed from the binomial coefficients at the previous level. For n minus 1, it's this plus this. You can prove this formula directly. Do it yourself. Just write it in terms of factorials. You'll get it. But let us give an alternative, a combinatorial proof. The left-hand side, n choose k, is the number of ways to invite k friends out of your n friends for the party. Let's say you have friends Leo, Sandy, Shu, Isabel, and so on. N friends total. You would like to invite k of them, and that's how many ways are there to do that. Now let's compute this same number in a different way. Let's decide if we're going to invite Leo or not. So the number of ways to invite the friends breaks down into 2 quantities. First, it's a number of ways to invite the k friends, not including Leo. And then there are a number of ways to invite the k friends for the party, including Leo. So we just break down the total number of ways into 2 possible cases. In one, we invite Leo. In the other, we don't invite Leo. All right? How many ways are there to invite k friends, not including Leo? In this case, if Leo is excluded, then we just have n minus 1 friends, really. We just say Leo is not our friend, so it's not going to be invited. So the number of ways to send out invitations will be n minus 1 choose k, because now we're choosing from n minus 1 friends. Good. How many ways are there to invite the k friends, including Leo? Well, first we invite Leo already, we know that. And now we need to decide who else to invite from n minus 1 friends. We already invited Leo, so we have to invite just k minus 1 more friends. Done. We proved Pascal's identity. Pascal's identity can be organized visually in the following way, known as Pascal's triangle. Pascal's triangle looks like this. First, let me put ones this way, and then I'll fill the body of this triangle by summing. So here I sum this one, and I get a 2. Now I'm summing 1 and 2. I get 3. Summing 2 and 1. I get 3. Summing 1 and 3. I get 4. Summing 3 and 3 gives me 6. Summing 3 and 1 will give me 4. And the pattern is clear. Every level of Pascal's triangle is supposed to list all binomial coefficients. For instance, this level will list 4 choose k's, and this level will list 3 choose k's. To get a 4 choose k, I just sum the 2 binomial coefficients in the previous level. And that is that sum. Just think about it, you will see it's the same formula. Just practice for one more level. 1 plus 4 is 5, 4 plus 6 is 10, 10, 5, and this is 5 choose k. And 1, 5, 10, 10, 5, 1 are all binomial coefficients, 5 choose k, and we've seen them already. We've seen them over here when we expanded x plus y to the 5. It's 1, 5, 10, 10, 5, 1. All these binomial coefficients at level 5. To practice with this, expand x plus y to the 6th. What will be the binomial coefficients here? Compute them from the binomial triangle by summing like this. Have fun.